This is the first part of our discussion on colligative properties. Colligative properties are properties of a solution that are affected by the concentration of the solute particles. Okay, they're not, it doesn't matter what the type of the solute is, it's just the concentration of the particles is going to affect these properties. And the properties that we're going to be focusing on are vapor pressure, freezing point depression, boiling point elevation, and osmotic pressure. Okay, the first thing to think about is that when we add a solute to a solvent, the vapor pressure of the solvent is lowered. And it's lowered by a factor that is equal to the mole fraction of the solvent in the solution. So we call this relationship Raoults Law. And here the thing to just be aware of is that our mole fraction is that of the solvent. The reason I say that is because normally when we talk about mole fractions in a solution, we're talking about the solute. But here we want to focus in on the solvent. So here's an example. Here we have water, and we're going to add some ethylene glycol to it. And we're going to make a 20 mass percent solution. That's what the W/W means. That means that, let's get the pen going. That means that I have 20 grams of the ethylene glycol per 100 grams of my solution. Okay, now, so if I'm going to use Raoults Law, P of the solution is X solvent, pure vapor pressure of the solvent. Okay, I need mole fraction, so I need to basically take this mass percent, and what this basically is telling me is that for every 20 grams of the ethylene glycol, I have 80 grams of water. All right, I need a mole fraction out of this. Ethylene glycol has a molar mass of about 62 grams per mole. And water, of course, is about 18 grams in 1 mole. And so let's see what we've got there. I have 0.323 of ethylene glycol and 4.44 moles of the water. Okay, so the mole fraction of my solvent, which is the water, is going to be 4.44 moles over 4.44 plus 0.323, and that's moles also. So that gives us mole fraction of 0.932. So vapor pressure of the solution is 0.932 times, and it didn't specify units, so we'll just keep it in kilopascals, and that's going to be 2.17 kilopascals would be our vapor pressure of the 20% ethylene glycol solution. Okay, when we have two volatile liquids that are mixed, we have a little adjustment we make to Raoults Law, because in this case both the solute and the solvent are going to be contributing to the vapor pressure. And so whenever we have a volatile solute, we have to look at the effect of both. And so what Raoults Law, the adjustment we're going to make, says that the vapor pressure of this solution is going to be the mole fraction of the solvent times the vapor pressure of your pure solvent plus the mole fraction of my solute times the vapor pressure of my solute. Now, when we have the two liquids, it's really not going to matter which one we consider the solvent and which one we consider the solute. Typically, the one we have more of would be our solvent, but for this calculation, it's really not going to make any difference. So we have the two liquids present, and it says that the vapor pressure, and I'm going to separate out our things here, kind of organize our information, and then we have heptane. And the pentane, my P0 is 56 kilopascals, and my P0 of my heptane is 4.8 kilopascals. And it says we have a concentration of 30 mole percent pentane. So that means I have 30 moles of the pentane per 100 moles of both. Okay, so that means then that I've got 30 moles pentane to 70 moles of the heptane. So in this case, we would think of the pentane as being our solute, the heptane being the solvent. So vapor pressure of my solution is going to be mole fraction of the solvent. So I have 70 over 100 times the 4.8 kilopascals plus 30 over 100 times the 56 kilopascals. Okay, so we have plus 0.3 times 56. So I'm getting 20.16 kilopascals. And that falls in between the vapor pressures of both, and it's a little bit closer to the vapor pressure of the solvent, which is what we would expect. Okay, here's just something to take a look at, to kind of again look at the effect of a solute on the vapor pressure. So say, for instance, we have these two solutions, and we're going to seal them up in this container, two solutions in a beaker. And then solution A has a higher concentration, and solution B has a lower concentration. Okay? So higher concentration is going to be lower vapor pressure. So here, solution B would have the higher vapor pressure. And that means that we're going to have an increased rate of evaporation from B. And then, again, they're going to recondense. And so, because B is evaporating more rapidly, but the recondensing is going to kind of take place at the same rate for both containers, then we would end up where the container A would start increasing because it's not evaporating as much, but it's condensing the same. B is evaporating more, but condensing the same, so the volume of B would go down until their concentrations are both the same, and then their vapor pressures would be the same, and so the rate at which they were evaporating and then recondensing would all be the same.